Linear approximations has really big applications, shockingly very, very big applications in mathematics and a lot of stuff that our programs and things do for us, or at least engineers and stuff like that. So the idea is we might be able to find a tangent line to a point close and use it to approximate a value that's also close to it. So we might be able to create a tangent line here. And you'll see the distance between the tangent line and the real function isn't that far away for a while. As you get further and further out, though, you'll notice there's a bigger gap. So if we have the equation of this line, and let's just say we wanted to find out this value, which is close to A, it's close to this one, and we want to find the measure of this value, we can just plug it into the equation of the tangent line. We don't know the function, this blue function here. We can plug it into the equation of the tangent line, and it's going to give us a pretty close value within reason. But obviously, the further and further away you get, if you're going to want to estimate the blue graph, you don't want to plug it really far away from that point of intersection, or it's going to be a really bad approximation. Now, why would they do this? There's calculators, for those difficult decimals. Well, several reasons. One, someone had to design the calculators. And that takes some of this programming inside to come up with the values that the calculators give you. Another reason is sometimes we don't actually know what the blue curve is. We don't know the actual function. We just have a derivative function and some initial value. And we're able to figure out what f of a is by using a bunch of tangent line approximations. Like we can use this tangent line to approximate this value to create its own tangent line to approximate this value, and so on. So there's actually a lot of applications, and this is a very useful thing. So how do we do it? We're just going to write the equation of tangent line all over again. So I told you it's important. You got to know how to write the equation line. That's what we're going to do. So you're just going to write the equation line, plug it in, and that's going to give you a close approximation to the point you're trying to evaluate. So let's look at an example. It might make more sense. So let f be a differentiable function with f of 2 equals negative 3 and f prime of 2 equals negative 4. So let's just say for some reason we know this information. And we want to estimate the value of f of 1.9. So we don't know what f of x is, but we can approximate something close to when x is 2. Remember, we want it to be close to this value. If we go far off, it gets a little inaccurate. So we're going to create the equation of the tangent line at x equals 2. So y minus y1 equals m times x minus x1. So this is your x1, y1. So we're going to have y minus negative 3 equals m times x minus 2. And where do we get m? M is our derivative. It's our slope. So this should be hopefully some review there. So that's the equation of our tangent line. Great. Okay, well now we need to approximate it at 1.9. So we're going to use this to approximate our function. So we basically have this line here. And we're going to use that line to approximate what the blue graph is really close to that value. You notice 1.9 is really close to 2. So we're approximating really close to that value. So I'm going to plug the 1.9 in. So this is y plus 3 equals negative 4 times 1.9 minus 2. 1.9 minus 2 is negative 0.1. Times that by negative 4 becomes a positive 0.4. That's quite easy. Sometimes you might need a calculator for these. Not so much with this one. Subtract the 3, and I believe that would be negative 2.6. And there's our answer. This one, same idea. You're just approximating at negative 3.2. So you're going to find the equation of the tangent line, plug in a negative 3.2 at the end, and evaluate. Here's one that's a little bit different. They're saying the local linear approximation of the function x equals negative 2 is this. So they're giving you the tangent line. What is the value of f of negative 2 plus f prime of negative 2? So f prime at negative 2. So if you remember, if you have some function, let's just say this is where x is negative 2. The tangent line there has the same slope as the graph there. So the slope of the tangent line is the same as the derivative of the graph at that point. So the slope of this tangent line is going to represent the f prime of negative 2. Okay, great. But also, the point of intersection on the tangent line is the exact same as the function. See that? That's the one time it's the same, right? Well, I mean, it might be the same over here, but at that spot, we know for sure it's the same as the function. It shares that same output with the function. So y equals 3x minus 5. Let's plug in the negative 2 to figure out what our function equals. So y will equal 3 times negative 2 minus 5 would be negative 6 minus 5, which is negative 11. Negative 11 plus 3 is negative 8. So we can figure out what the actual value is there by plugging it in, and then the slope is just the derivative. So it's not too big of a deal. And that's it. That's that assignment. I think this one's the same idea. You're going to find the actual function value by plugging it into the tangent line to figure out what the output is there. And then the slope of it is the derivative, negative 4.